Okay, well then we'll go ahead and start. Just a heads up to those listening in. Thank you so much for joining us. We'll be recording the presentation, so if you prefer to have your cameras off, feel free to do so. And also as a reminder, the Zoom software records all chats, including even private chat. That is not a setting we're able to change one way or the other. It's our pleasure to invite Dr. Nan Zhang to speak to us today, who is Professor of Information Technology and Analytics in the School of Business at American University. Its research focuses on data analytics and information security and privacy. He's received multiple awards, including communications at the ACM Research Highlight in the year 2020, the ACM Sigmund Research Highlight in 2019, NSF Career Award in 2008. Of note, he served as a program director at the NSF with responsibilities in information integration and informatics, secure and trustworthy cyberspace, and big data programs. He's going to be talking to us about a really interesting aspect of privacy. As some of you might know, we all here at UCSD have several faculty members involved in privacy preserving computation and the implications of privacy in healthcare data. And one of the things I've always been curious about is what are the implications of some of these privacy preserving and anonymization techniques on the actual data itself and the analytics that may be done with that data. So thank you very much, Dr. Zhang, for joining us in the seminar.
Thank you so much for the warm introduction. It's really my pleasure to be here and to share with you some of our recent research on the implications of data anonymization on disparity detection, specifically on the kind of statistical evidence that is commonly considered as evidence of disparate impact today. Now, I want to start my talk with just kind of two disclaimers, if you may. One is the tenor of this talk is really less about saying whether data anonymization is good or bad for detecting disparity, but more of illustrating the intricacy of the interactions between the choices you make on how you anonymize your data and the choices you make or the choices, let's say, a third party makes on what kind of statistical evidence are admissible to demonstrate the existence of disparate impact. So that's the first disclaimer. So we really want to illuminate the intricacy of this interaction more than kind of draw an up or down vote on whether it's good or bad. Now, the second disclaimer that I want to make here is if you look at the state of the art and the state of the practice for privacy protection, especially as it pertaining to, for example, anonymizing healthcare data, public health data today, there's really a pretty significant gap between the state of the art and the state of the practice. The research community would have certain prevailing views on which are good mechanisms for privacy protection. If you look at public health officials, state agencies, they use completely different methods for anonymizing data. A direct implication of that is when we talk about anonymization, it's very easy to get drawn into the specific arguments, mathematical arguments on how a specific anonymization mechanism works. So instead of kind of getting into that detailed level of arguments, what I want to do today is to focus most of the talk on the conceptual level to demonstrate why different types of anonymization design could have different impacts on the statistical evidence for disparate impact. Now, of course, later in the talk, I will show you some mathematical results and some empirical examination over real world data, but most of the talk, I hope, will stay at the conceptual level, so there is an intuitive understanding of how the anonymization technique interacts with the statistical evidence for disparate impact detection. Now, why is this an important topic? Why is data anonymization of interest? Now, a lot of recent interest in data anonymization is actually spurred by the new privacy regulations Europe has GDPR, and California has CCPA, and California also recently, just a few days ago, passed an even stronger version of their consumer privacy regulation laws. So a lot of these privacy laws exempt data, let's say, that the processing of consumer data if such data have been properly anonymized. Which means that if the company, after collecting your data, anonymize the data before they store it, then they don't have to notify you every time they decide on how to use that data. So that makes anonymizing data starting to make sense, in the sense that the company doesn't have to go through the burdensome process of notifying each and every customer before they can use their data. So long as the data is anonymized, it's not within the scope of these privacy regulations anymore, and the company can feel free to use it. So that's a major motivation for privacy protection, for data anonymization in particular. Now, what we want to examine here is, of course, how data anonymization affects disparity detection. That is, if in the future, and one organization itself, or let's say a third party, wants to examine whether there's disparate impact against a disadvantaged subpopulation based on the data that has already been anonymized, then what's the implication of data anonymization on the feasibility of identifying statistical evidence for such disparate impact from the anonymized data? This is particularly relevant in the context of healthcare because, I guess, as many of you are very familiar, health disparity is an important topic in public health. And as has been argued in this article, and also has been argued by these folks at the NIH Institute on Minority Health and the Health Disparities, a critical challenge facing the understanding of health disparities today is that many health data were collected without the social determinants information, which means that a person's, let's say, gender, age, race, income, demographic information, that is important for us to understand whether there's disparate impact in the demonstrated by the data against certain disadvantaged populations. But on the flip side of this argument, it's also easy to see that when, let's say, health disparity researchers call for the inclusion of social context information in the collection of health data, we can also at the same time saying that this is calling for the collection of personal identifiable information, or at least information that is known as quasi-identifiers that can help identify individuals. This is calling for the collection of that kind of information when the underlying data, the public health data, the healthcare data is highly sensitive. So just this argument of what is important for health disparity research, that is the collection of social context along with healthcare data, demonstrates to you that there is this intrinsic tension between privacy protection, data anonymization, and the disparity detection, because at the same time, you are enabling a lot of public health research by collecting social context data, you could also potentially threatening the privacy of these individuals from whom the information is collected, because you are collecting their potentially identifying information alongside very sensitive data. Now, to make this matter even more serious, this is the result of a Pew survey back in 2017. Now, what it demonstrated was that people who are traditionally considered as in the disadvantaged groups are actually more concerned about the protection of their personal information. In this case, you can see that people who earn under $20,000 a year are actually the group that has the highest concern about the privacy of their information. So this group tend to feel that they have already lost control of their private information, as they don't know how such information is used. They don't know whether it can be used against them in the future. So essentially, this forms the tension between disparity research and data anonymization, or more generally privacy protection, because the very group of people who the disparity research aims to help, which is the disadvantaged subpopulations, are also the same group of people who are most concerned about their privacy and who could actually get the most harm from the disclosure of their personal information, from being identified from the data being collected. Now, in order to understand this interaction between privacy protection, in particular data anonymization, and the disparity research, now what we first want to do is to get kind of a big picture understanding of what exactly is the kind of information that people are, or health disparity researchers, or more generally disparity researchers are looking for in a data set. And also we want to get a big picture understanding of what kind of techniques are commonly used for data anonymization. So once we get these big picture views of the different types of statistical evidence commonly used for disparity detection and the different types of anonymization techniques commonly used to protect privacy, we can then examine the interactions between the two. In terms of the statistical evidence commonly used for disparity detection, we can roughly partition the statistical evidence into two types. Now, these types are usually used in different disciplines for the identification of different types of disparate impact, but you can also see some disciplines that use both types. So we call them disparities through separation and the disparities through variation. I'll show you some examples and the definition in a minute, but generally speaking, we can say that if you look at academic research today, sociology researchers tend to focus on those statistical evidence showing disparities through separation, while in epidemiology, the focus appears to be on disparities through variation. Now, perhaps because of such disciplinary differences, if you look at the court cases that is currently decided in the courts, they also tend to follow different principles in terms of the kind of statistical evidence they look for in establishing the existence of disparate impact. For example, in a lot of employment discrimination litigations, perhaps because of their reliance on, let's say, research in sociology, research in industrial organizational psychology, a lot of these court cases actually use the principles alongside the idea of disparities through separation. So I'll show you in a minute how it is defined. On the other hand, for the court cases that kind of are closer to epidemiology, for example, the toxic tort cases, the tort litigations, they tend to follow disparities through variations definitions. So what are these two types of statistical evidence for disparate impact? In terms of disparities through separation, now this is a code from pretty famous legal case involving employment discrimination. Now, as you can see from this quotation, the general rule here is that the disparity must be greater than 2 or 3 standard deviations difference between the minority population and the majority population. So generally speaking, this kind of statistical evidence is looking for the statistical distinguishability between different subpopulations. On the other hand, what happens with disparities through variation, as you can see in this case, this is actually also in the area of employment discrimination, but instead of used in litigations, used in the court system, this is a quotation from the EEOC uniform guidelines, the kind of recommendations of what can be considered as disparate impact. Now, if you look at this definition, what it cares about is not the statistical distinguishability between different subpopulations. Instead, what it cares about is the absolute difference between different subpopulations. So in this case, it is to say that if the selection rate for one subpopulation is less than 4/5, 80% of the selection rate for another subpopulation, then there's potential disparate impact. So if we put them side by side, you can essentially see the fundamental differences between these two types of statistical evidence for disparate impact detection. Now, disparity through separation, those following the standards established in the court system for employment discrimination, for example, tends to stress on whether there is sufficient evidence demonstrating the statistical distinguishability between the different subpopulations, which means that if you follow this kind of statistical evidence, you need to care about not just the mean outcome for different subpopulations, you also need to care about the standard error of these sample mean estimations. Only when the difference between sample means exceeds 2 or 3 times the pooled standard deviation can you confidently say that there is sufficient statistical evidence for disparate impact. Now, on the other hand, if you care about disparity through variation, then really the only thing you care about is the absolute difference between the mean of different subpopulations. You look at any outcome measure, be it the healthcare quality, be it the selection rate in personnel selection in employment discrimination cases. If you adopt the disparity through variation definition, then what you care about is really the ratio between the sample means and has nothing to do with the standard deviation of each subpopulation. Now, the different kind of doctrines followed by these two types of statistical evidence directly lead to these kind of differences in their conclusions, as demonstrated on this slide. So, if you look at, for example, the 4 demonstrations on the left-hand side, right? The first one and the third one share the exact same sample means. Right? So the sample means are quite different from each other for the 2 subpopulations. Now the second and the fourth one share the same sample means. So in this case, you can see the 2 subpopulations have sample means pretty close to each other. Now, what this means is if you only care about disparity through variation, then you're going to say that the first one and the third one perhaps have demonstrated evidence for disparate impact, while the second one and the fourth one did not, because the absolute ratio between their sample means are not as large as the first and third cases. However, if you care about the disparity through separation definition, then what happens is you need to look at not just the sample mean difference, but also their standard deviation as well. Now, in this case, what we can see is that in the second case, for example, because the standard deviation of these 2 subpopulations are drastically smaller than, for example, in the other 3 cases. Now, what happens is, even though the absolute sample mean difference is small, there is still enough statistical evidence to distinguish between the 2 subpopulations because their standard deviation is also small. So their sample mean difference exceeds 2 or 3 times pooled standard deviations. So in this case, if you follow disparity through separation definitions, you would say there is evidence for disparate impact, even though the disparity through variation definitions would argue otherwise. Similarly, if we look at the third case, now we just said this disparity through variation definition would consider this to have evidence of disparate impact because the sample means are quite different from each other. However, what happens in this case is that the standard deviation of the 2 subpopulations are also quite large. So if you follow disparities through separation definitions, then what happens is that even though the sample mean difference is large, it is not as large as 2 or 3 times the standard deviation. So the result of that is you cannot find sufficient evidence for disparate impact. So even though disparities through variation would consider there to be evidence for disparate impact on the third case, the disparities through separation definition would argue otherwise, saying there isn't sufficient evidence for disparate impact. So this demonstrates the fundamental differences between the two kind of doctrines of thinking about what constitutes statistical evidence for disparate impact. And as I said, generally speaking, sociology research, psychology research, and employment discrimination court cases follow the disparities through separation doctrine and look for this 2 or 3 standard deviation as the difference. On the other hand, if you look at the epidemiology literature, or if you look at the court cases related to toxic tort litigations, then usually they follow the disparities through variation doctrine and use measures like odds ratio, which really just look at the difference between sample means and not exactly their standard deviations. There has been actually extensive arguments in the literature regarding the pros and cons of the two types of definitions. So as you can readily see from this demonstration, now one argument is that if you follow disparities through separation, you are essentially penalizing those large organizations. Because, well, as we all know, the standard error of sample mean estimation decreases with it's inversely proportional to the square root of sample size. So the larger your organization is, let's say the number of individuals in your organization is N, then the larger N is, the smaller the standard error will be. The standard error will be proportional to 1 over square root of N. So as a result of that, the more likely people will see statistical evidence for disparities through separation from the data set. So there were arguments that the disparities through separation doctrine is unfairly punishing those organizations with a large sample size. Now, on the other hand, as you can see, disparities through variation does not really care about the sample sizes. So it has been argued that it might be a better measure or a better indicator of disparate impact than disparities through separation. However, it also runs into the possibility that when the standard deviation is too large, then maybe a large odds ratio that you observed could be just a result of chance rather than indicating the real existence of disparate impact in the data set. Now, notwithstanding those debates on which kind of definition is better, now what we want to examine next is what happens when you use either type of definition to examine anonymized data. Does the choice in terms of the type of statistical evidence you are looking for in examining disparate impact actually affect how the anonymization of data affects the outcome of your examination? So next, we're going to look at the different types of anonymization techniques that you can apply. Now, just like we partitioned the space of statistical evidence for disparity detection into two categories, we can similarly partition the types of state-of-the-art and state-of-the-practice data anonymization techniques into two categories, which we refer to as data removal and noise insertion, respectively. Now, as you can imagine, these are two very natural ideas when you think about anonymization. When you think about anonymizing data to protect the privacy, now one immediate idea is let me remove from the data set those information that may not be essential for whatever way I want to use the data for. So this essentially is data removal. Let's try to remove part of the data so that the remaining part is the minimum necessary amount of information required for whatever purpose that I want to examine the data for. Now, another idea is to say that instead of removing part of the data, what I'm going to do is I will insert some random noise into the data so as kind of to hide a tree in the forest. If I add enough random noise into the data, then no one would be able to re-identify or recover the original real data values from the anonymized data set. Now, some examples of each type of techniques, I guess many of you have seen these kind of techniques before, have heard about them. For example, if you remove all the personal identifiable information from a data set, or if you use techniques like K-anonymity, which is to ensure that for every individual included in the data set, there must be at least K-1 other individuals who have the exact same published attribute value combinations as the given individual, and many other techniques. These kind of techniques all belong to the data removal category because they are removing part of the data set in order to fulfill the anonymization requirements. On the other hand, if you simply add random noise to the data, or if you have heard about differential privacy techniques, a lot of differential privacy techniques also achieve privacy protection through noise insertion. So those are very popular type of techniques for anonymizing data. Now, this is actually a real-world example of how state agencies anonymize their data set. So this is a procedure used by the Texas Department of Health to anonymize their inpatient discharge data set before they release such data sets to the public. I will not go through all the rules listed here. However, it's very easy if you just look at a few of them to see that these rules are very typical data removal rules in the sense that it is not trying exactly to change the values of data. It won't change, for example, the age of a patient or the kind of disease reported for a patient. Instead, what it is trying to do is to remove certain information from the data set, like the last 2 digits of zip code, if the patient is not coming from a very popular zip code in the state, or to remove the entire zip code by changing it to 88888, or removing, let's say, county information, race information, etc. So this is kind of a state of the practice technique that people tend to use. Now, if we consider data removal technique in particular, now a general idea of data removal is to remove the part of the data set that is not very popular. Now, it's important to understand this because this abstraction of data removal techniques essentially determines how it interacts with the statistical evidence for disparity detection. So you'll see in a moment, we'll talk about their interaction, but what this slide shows is this tenor of data removal techniques. It's the idea of trying to remove part of the data set that is, let's say, not very popular and therefore more likely to be unique and more likely to be identifiable. So just a very simple example. In this case, if you consider there to be just one variable in the data set and the left-hand side shows the histogram for the data set, then a lot of data removal techniques, what they are going to do is they look at the histogram and they say that I will set a threshold for the frequency of a value. And if the frequency of a particular value drops below this threshold, I'm going to remove every record with that value because it's not popular, is more likely to be unique, is more likely to be identifiable. So similarly, if we broaden the scope a little bit by considering not just one dimension, but multiple dimensions, this is a typical example. Essentially, if, let's say, an individual's record has someone else in this neighborhood, meaning that there are some other individuals' record that are pretty close to this individual's, then we can say, you know, the individual is perhaps safe because it's not easy to uniquely identify this individual. However, if this individual's record is nowhere near any other individual in the data set, then we would say that, you know what, maybe it's dangerous to release this individual's data set because it's unlike anyone else and therefore is more likely to be uniquely identified. So think about what happens when our underlying idea is to remove those individuals that looks unique. Now, if you look at this figure, this demonstrates to you what's going to happen, right? We are going to just remove those individuals for whom there's no one else in this neighborhood. So that is a key idea used by many data removal mechanisms. On the other hand, what noise insertion does is much simpler. Instead of saying, let's take a look at whether there's anyone else in the neighborhood, or which is more likely to be identifiable, which is less unique. Now, noise insertion can say that, let me just add random noise into the data set so that each individual's value will change, and therefore it's difficult, if not impossible, to recover the original value from the perturbed values. Now, this essentially illustrates why the difference in the underlying ideas of the two mechanisms actually would have very different implications for the detection of disparate impact. Now, in this case, again, this is a highly simplistic view, but if you think about the principles these techniques follow, this view will become quite straightforward. That is, what data removal is trying to do is essentially, you can say, to squeeze the distribution, to make the distribution more concentrated on the popular values, for the simple reason that those unpopular values, those less popular values, are more likely to be identifiable, and therefore they're more likely to be removed from the data set. So after data removal, the distribution tends to be less dispersed, tends to be more concentrated than before. This is the exact opposite to what happens after noise insertion, because noise insertion, by definition, adds random noise to the data. So the distribution, if you take it at face value after noise insertion, of course, is more dispersed than what it was before. Now, what I would like you to consider is, given the different implications of these two different anonymization techniques, what will happen if we use the disparity through separation definition? If we define disparate impact, if we want to identify disparate impact through statistical evidence as defined by disparity through separation. Now remember, disparity through separation actually cares about not just the sample mean difference, but the standard deviations of different subpopulations. Now, if we use data removal techniques so that the standard deviations of these different subpopulations actually are reduced after anonymization, for the simple reason that those less popular values tend to be removed. Then what happens is, it will be more likely for the disparity detection algorithm to positively report the existence of disparate impact, because a reduced standard error means an increased probability of distinguishing between the two subpopulations. The exact opposite would happen if we use noise insertion. Because once we use noise insertion, what happens is the standard deviation of these subpopulations will grow rather than shrink. So because disparity through separation actually requires sample mean difference to be 2 or 3 times the standard deviation, it will be less likely for it to report positively the existence of disparate impact. So in other words, what's likely to happen after data anonymization is, if you use the data removal techniques for data anonymization, then disparity through separation is more likely to report a false positive result. So it's more likely to raise a false alarm, because the standard error that you observe over the anonymized data is likely to be smaller than the standard error in the original data. And as a result, there's a possibility of false positive. On the other hand, if you take the results at face value and then after noise insertion and then apply disparities through separation definitions, then false negative is a more likely outcome. Because what happens is the standard error gets much larger and is less likely for the disparity detection algorithm to report a positive result. This essentially demonstrates what happens if you use the other disparity definition, disparity through variation. Now, as you can imagine from the previous slide's discussion, in the previous slide, what we discussed is because data removal and noise insertion have different effects on the standard deviation of the subpopulations, they have different effects on the outcome of detecting disparities through separation. Now, remember, we talked about earlier, disparities through variation definitions like the odds ratio that I believe many of you are familiar with has nothing to do with the standard deviation. They care only about the sample mean difference, the sample mean ratios. So what will happen in this case, as you can imagine, is that, well, it can go either way after anonymization. And this figure demonstrates exactly that. So if we use data removal as the technique, again, as we discussed before, what data removal wants to do is to remove those individuals that has no one similar to him or her in the data that is being reported. So if we look at the top left corner here, now in this case, let's assume that the red points are the minority population, the blue points are the majority population. Now, what happens with data anonymization is if you look at the red points on the right half, then there's really no other red points around it. Right? And all the points around it are different from this point in terms of their group affiliation. So a data removal algorithm would look like this and say that for these 4 red points, they don't have anyone similar to them in their neighborhood, so they will be removed. Now, after data removal, you will essentially get a result like this. Now, if we consider the x-axis to be the outcome variable, then what happens is before data anonymization, the mean outcome for the majority and minority population are both 2. Which means there is really no disparity. The ratio is 1. But after anonymization, what happens is these 4 data points are removed because they don't have anyone around their neighborhood. And yet these 4 points remain there. So the mean of the majority, the blue population, is still 2, but the mean of the red minority population became 1. So the ratio become 2 or 50%. Rather than the 100% as before data anonymization. Now, this goes one way, and it could also go the other way. If we look at this example here on the bottom left corner, now what happens here is that before anonymization, there is actually disparate impact because the mean of the majority population is 1, the mean of the minority population is 2. Okay? However, the exact same logic applies because these 4 red points to the right don't have anyone around their neighborhood. They get removed after applying the data removal technique. So after anonymization, what happens is each subpopulation, either subpopulation's mean becomes 1. So while there was disparate impact, evidence for disparate impact before data removal, there's none after data removal. So these 2 examples here really demonstrate to you that if you adopted the definition of detecting disparities through variation, then applying data removal technique could really go either way. It could generate false positive, like which we demonstrate in the first case. It could also generate false negative, like which is demonstrated in the second case. So that is essentially the interactions that I talked about in the beginning of this talk. The interaction between the 2 types of techniques for anonymization, data removal and noise insertion, and the 2 types of definitions for disparity detection, either through separation, that is 2-3 times standard deviation, or through variation, the more likely than not, or the odds ratio measure. Now, in this case, if you adopt the definition of disparity through separation, then data removal is more likely to give you false positives than false negatives. Noise insertion, on the other hand, is much more likely to give you false negatives than false positives. On the other hand, if you adopt the definition of disparities through variation rather than through separation, then what happens is the false positive and false negative could both happen for both types of techniques. In particular, for data removal, as we demonstrated through the two examples, whether you get false positive or false negative really depends on the data distribution. For noise insertion, on the other hand, in many cases, you can actually prove that false positive and false negative are equally likely over the data set because of how noise are inserted into the underlying data. Now, this is essentially the main takeaway from our findings. That is the effect of data anonymization on the outcome of disparity detection really depends not just on how you anonymize the data or what kind of statistical evidence you are looking for in terms of disparity detection, but this interaction between the mechanism you choose for anonymization and the definition you follow for disparity. So far I have focused exclusively on the conceptual discussions of what's the underlying reason for this interaction. Now, we also have some more formal mathematical results in terms of why the interactions are what we claim to be in the previous table. So I won't go through all the details here, but essentially the first theorem is saying that if you use a data removal technique like k-anonymity, what happens is the standard error actually is proportional to 1 over the square of k, which means that the standard error gets smaller after data anonymization. And as a result of that, the likelihood of generating a false positive is higher, the more stringent your privacy guarantee needs to be. Now, theorem 2, on the other hand, is to demonstrate that if you follow data removal technique and you use a disparity through variation technique, then again, the variation could go, the outcome bias could go either way in terms of the outcome of disparity detection. Now, the third theorem is to show that if you use a noise insertion technique, in particular, a epsilon delta differential privacy algorithm, then what happens if you use a disparity through separation definition is that the statistical power of your disparity detection algorithm will be lower. So here is an upper bound on the statistical power. So as you can see, the lower your statistical power is, the more false negatives you generate. So what this means is that you might miss some real disparate impact if you use a differential privacy technique along with the disparity through separation definitions. Now, of course, as you can see from this more pretty complex formula, exactly how much false negatives you are going to generate, or exactly how low the statistical power becomes, actually is a pretty complex function depending on the sample size, depending on how stringent the privacy guarantee you need to achieve. Now, what we did was we actually did some kind of back of the napkin calculations on whether the legal cases, the court cases that actually proceeded in the court during the last few decades. For those cases, if, let's say, differential privacy has been applied over the input data set, would it still be possible for the kind of disparate impact that was admitted in court as evidence of disparate impact, would it still be discoverable from the underlying data set? Now, again, as I said, this is a back of napkin kind of calculation. So what we did was we start with the assumption that we want the detection of disparate impact to have a power of at least 0.8. You want the statistical power to be at least 0.8. On the other hand, you want the type 1 error rate, the false positive rate, to be at most 1%, roughly translating to 3 times the standard deviation, often used in court. So essentially, once you set these two parameters, you can derive a threshold according to the effect of differential privacy. Now, what we end up proving was that if you want to achieve epsilon equal to 0.01, which is a kind of acceptable level of anonymity or privacy, and then the number of cases in the data set that can flip without changing the outcome of disparity detection must be at least 438. So what does it mean? It means that, for example, if you are investigating whether there is a promotional, there's a difference in promotion rate among male employees and female employees in an organization like the Wermuth v. Dukes case here, then there are what this bound of 438 means is that the data set has to satisfy the following condition. That is, even if you change the promotion outcome of 438 employees, like 438 female employees, female candidates who wasn't selected for promotion, even if you change those to those employees being promoted, there must still be a difference between the promotion rate of male and female employees in the data set. And so the difference has to be at least 438. Now, here we actually listed the actual difference in these real-world court cases, and as you can see, none of it is actually as much as 438. So that basically shows that these loss of statistical power could actually matter if the sample size of the data set that you use are not very large, at least for those that are approximately the same size as those data sets that were subject to litigation, as in these real-world cases. It seems that the sample sizes are not really large enough to sustain a anonymization with differential privacy of epsilon equal to 0.01. Now, we also validated these findings, not just through the mathematical proofs, as I showed you a moment ago, but also through an empirical examination over a real-world inpatient discharge data set. So what happened was we took the inpatient discharge data set of a state other than Texas, because Texas only released the result after their anonymization. So we took a state that doesn't apply those anonymization procedures as Texas, and then we applied the procedures Texas used over the data set from the other state. Now, most of those rules actually do apply because those identifiers are pretty similar across the states, like 17 out of 20 state-level inpatient data sets in AHRQ share the exact same set of identifiers. There are a few rules that are Texas specific, like Texas is a border state, so they have specific rules for visitors from other countries, but there are very few in the data set that we examine. But by and large, we follow the exact same set of rules defined by the Texas Department of Health over the data set that we had access to. So these are just some statistical information of the data set that we tested. Now, after that, what we did was we followed the standard procedure for detecting disparate impact as used in the existing literature, either through the disparity through separation definitions or through the disparity through variation definitions. So in this case, is the disparity through separation definition along with the data removal techniques. So what I would like to show you here is that overall, as you can see, for k-anonymity, if we apply k-anonymity, which is a data removal technique, over this empirical data set, then we only see false positives from the outcomes. Now, if we apply the Texas procedure, we do see both false positives and false negatives, but there are more false positives than false negatives for disparity detection from the data set. That essentially verified what we presented in the table. That is, if you use data removal as the anonymization technique and you follow disparity through separation, you are more likely to see false positives than false negatives. Now, in this case, what we did was to still use data removal, but then we consider disparity through variation techniques, definitions, in particular, the odds ratio and the legal doctrine of more likely than not. That is, what we want is the ratio between the two subpopulations must be at least 200%. Okay? More likely than not, principle. Now, in this case, as you can see, we just like what we predicted before, when you use disparity through variation definitions, then it could go either way after anonymization. So there are a fair number of false positives. There's also a fair number of false negatives after applying the data removal technique. Now, for noise insertion, we implemented two state-of-the-art algorithms for either the disparity through separation definition or the disparity through variation definition, because depending on which one we use, we can optimize the differential privacy algorithm accordingly. So on the left-hand side, what you see is the result of applying differential privacy when adopting the disparity through separation definition. And in this case, just as we predicted, there was no false positive and only false negatives. Okay, so the statistical power was indeed lower, you can see that for race equal to African Americans, now the statistical power of disparity detection actually dropped to just 2%, even when we have a pretty lenient privacy guarantee of epsilon equal to 1. Similarly, even if we consider gender, the statistical power dropped to 11% for the, again, for epsilon equal to 1, which is a, let's say, not so satisfactory privacy guarantee. Now, on the other hand, if we apply the disparity through variation definition, then just as we predicted, it could go either way. There were some false positives, there were some false negatives, just like what you see on the right-hand side of this table. So just to conclude, once again, the important message that we want to convey through this study is not so much as whether anonymization is good or bad for disparity detection. Certainly there is an inherent trade-off between the how stringent your privacy guarantee you want it to be, how stringent you want the anonymization to be, versus how much statistical power you want left in terms of detecting disparate impacts from the data set. So the key takeaway message we would like to have from this study is that there's this intricacy in the interactions between the type of mechanisms you use for data anonymization and the kind of definition you follow, the kind of statistical evidence you admit for disparate impact. In particular, while data removal would create false positives for disparity through separation definitions, differential privacy or other noise insertion techniques would tend to create false negatives. If you use disparity through variation rather than disparity through separation definitions, then you would likely see both false positives and false negatives in the result. So we believe it is important for organizations to be aware of this interaction before they either decide on how to anonymize their data or they decide on how to examine and anonymize the data set to identify statistical evidence for disparate impact. So thank you, and that concludes the talk.
Great, well, thank you very much, Dr. Zhang. Many questions from the audience, if you have a few minutes. Please feel free to maybe type the questions in, and I'm happy to ask on your behalf, or if you'd really like to ask with your own voice, you're welcome to unmute your. While we wait for any questions, I had one, if you don't mind. I think your presentation and both your empirical analysis and the theoretical one, it seemed like there was an underlying assumption of a parametric model. And I'm wondering what would be any implications for parametric comparisons or non-parametric models, whether it be a standard, what we might call a statistical technique, such as say Wilcoxon, or even a non-parametric machine learning technique, such as random.
Well, that's a great question. So what we wanted to do in terms of the empirical examination was not to say that the kind of techniques we use for disparity detection are necessarily the best techniques for disparity detection. Instead, what we wanted to do was to simulate to the extent possible the kind of practices people actually follow in practice to detect the disparity. And so for example, in implementing the disparity through separation definition, what we used is a regression analysis method that is commonly followed in sociology research when they are trying to detect the disparate impact over, for example, labor statistics and data sets. Now, I think you raised a very important question as of what would happen if we use other kind of methods to detect the disparity rather than the kind of disparity detection method that has been used in the sociology literature or in the epidemiology literature. Now, I think there are 2 points that I want to make here. One is the mathematical proofs that I showed earlier. For example, let me go back to this slide. This result here is really independent of any kind of disparity detection method that you want to use. Instead, what it is saying that whatever method you want to use, if you want to achieve statistical power of 80% and type 1 error of less than 1%, then the data set has to satisfy this difference lower bound of 438 when you want to achieve differential privacy of epsilon equal to 0.01. So this is agnostic to whatever method that one would like to use to detect the disparity. Now, of course, this kind of bound would not be as tight as what you would see if you consider just a specific kind of method. So the second point I want to make here is that exactly as you said, what the empirical results seemingly suggest is that the kind of techniques, the kind of methods that people, either researchers or practitioners, tend to use today to detect the disparity from anonymized data set needs to be more carefully scrutinized and improved in the future. In the sense that, for example, if you look at the public health data set, how it is used in practice, a lot of researchers tend to use the data sets as if it has not been anonymized, as if it's the real data set. Now, what we demonstrated here is if you do that, then you're likely going to see false positives if you use disparities through separation definition, and you're likely to see both types of errors if you use disparity through variation definitions. Now, would it be possible for us to improve upon these methods? So instead of just taking the anonymized data at face value, instead developing better methods that can more accurately recover statistical evidence for disparity from anonymized data sets. I would argue that one, it is certainly possible, and second, it needs to be more carefully looked at than what has already been done in the literature. So I think it's an excellent question, and those two are kind of my thoughts on the method design.
Thank you very much. We had another comment and question with regard to generalization as anonymization methods such as k-anonymity, where it's not necessarily case removal as opposed to, I don't know if we would call it case aggregation, such as when you eliminate the last 2 digits of a zip code, perhaps. Could you clarify, since you're not really removing individuals, you're sort of clumping them into other groups, do those same issues remain?
Yes, absolutely. That's a great question. So one thing I want to clarify is the reason why I use the case removal as the demonstrating example in the conceptual development is just for its clarity. Now, the clarity stems from the fact that after you remove the data point, that no one knows its existence. But if you generalize the value of an attribute, for example, from the specific age of an individual to a range like 30 to 40, then how exactly the disparity detection algorithm treats this range becomes, let's just say, a matter of method design. Right? As I said in the very beginning of the presentation, I didn't want to get drawn into the specific discussions of individual methods. That's why I wanted to keep the conceptual discussion clear and simple by assuming the removal of data points. Now, one thing I do want to say is that the mathematical proof, on the other hand, did not assume case removal. Instead, what we considered is that if you achieve T-anonymity, essentially what you did was you made these T data points indistinguishable from each other. So that by design would reduce the standard error of the values in the anonymized data set. Again, conditioned upon the researcher using this data set taking the anonymized data at face value. So the mathematical proof is more generic, is kind of a generalized version of the conceptual discussions I had earlier, and is not limited to just case removal. But on the other hand, and just like in my last answer to the last question, I can't stress enough that all of these results are based on the assumption. The data removal results are based on the assumption that the researcher conducting disparity detection is taking the anonymized data at face value. Now, you might say there's a discrepancy here, right? Because just like in this slide, for differential privacy, we didn't assume so. For differential privacy, we assume that the disparity detection did take into account that differential privacy has been applied and actually try to recover the original statistics before applying the noise insertion techniques. So it's trying to get a maximum likelihood estimation of what is the odds ratio that is in the original data set. But we didn't assume so for the data removal techniques. So I want to say that number one, again, the purpose is really to simulate what is being done in practice, because researchers and practitioners using the Texas data set tend not to do an interaction for the anonymization technique. We wanted to follow that. And number two, I also want to point out that how exactly one can enhance disparity detection by not taking the data at face value and instead trying to understand what happens, what's the statistical evidence over the original data set. Just like I argued for the last question, is very important for future research, but it doesn't seem to have received a lot of attention from the research community. Now, one reason for that might be that if you look at the state of the art in data anonymization, people have largely moved on from data removal techniques. And the prevailing view is that differential privacy is kind of the state of the art technique, and almost all attention has been put over there. While there's also this gap with practice, because in practice, you also see Texas, you also see other states that use the exact kind of data removal techniques that I presented earlier in the presentation. So how to bridge this gap, how to understand the proper way of doing disparity detection over a data set anonymized through data removal, I think is an important challenge.
Thank you very much, Dr. Zhang, for a really fantastic presentation, and thank you everyone for joining us today.
Thank you.